Dear students, hello and welcome. Today I am going to deliver a lecture on what is thermodynamics, state of a system, state variables, intensive and extensive variables, thermodynamic equilibrium and first law of thermodynamics. Now let us first try to have a look at the main objectives of today's deliberation. Number first is to understand the concept of thermodynamics. Next is to explain state of a system and state variables. Number third is understanding the intensive and extensive variables. Next is explaining thermodynamic equilibrium, and finally we shall be discussing the first law of thermodynamics. Now let us start with the concept of thermodynamics. Thermodynamics is the branch of physics that deals with the relationships between heat and other forms of energy. In particular, it describes how thermal energy is converted to and from other forms of energy and how it affects matter. It defines macroscopic variables such as internal energy, entropy and pressure that partly describe a body of matter or radiation. It states that the behavior of those variables is subject to general constraints that are common to all materials beyond the peculiar properties of particular materials. These general constraints are expressed in the fourth law of thermodynamics. Thermodynamics describes the bulk behavior of the body, not the microscopic behaviors of the very large numbers of its microscopic constituents such as molecules. The basic results of thermodynamics rely on the existence of idealized states of thermodynamic equilibrium. Its laws are explained by statistical mechanics in terms of the microscopic constituents. Initially, thermodynamics as applied to heat engines was concerned with the thermal properties of their working materials such as steam in an effort to increase the efficiency and power output of engines. Thermodynamics was later expanded to the study of energy transfers in chemical processes such as the investigation published in 1840 of the heats of chemical reactions by German Hess, which was not originally explicitly concerned with the relation between energy exchange by heat and work. From this evolved the study of chemical thermodynamics and the role of entropy in chemical reactions. There are three principal laws of thermodynamics. Each law leads to the definition of thermodynamic properties which help us to understand and predict the operation of a physical system. The zeroth law of thermodynamics involves some simple definitions of thermodynamic equilibrium. Thermodynamic equilibrium leads to the large scale definition of temperature as opposed to the small scale definition related to the kinetic energy of the molecules. The first law of thermodynamics relates the various forms of kinetic and potential energy in a system to the work which a system can perform and to the transfer of heat. This law is sometimes taken as the definition of internal energy and introduces an additional state variable, that is enthalpy. The first law of thermodynamics allows for many possible states of a system to exist, but experience indicates that only certain states occur. This leads to the second law of thermodynamics and the definition of another state variable called entropy. The second law stipulates that the total entropy of a system plus its environment cannot decrease, it can remain constant for a reversible process but must always increase for an irreversible process. The third law states that the entropy of a pure crystal at absolute zero is zero. Entropy is sometimes called as waste energy, that is, energy that is unable to do work, and since there is no heat energy whatsoever at absolute zero, there can be no waste energy. A system undergoes a thermodynamic process when there is some sort of energetic change within the system, generally associated with changes in pressure, volume, internal energy, that is temperature, or any sort of heat transfer. There are several specific types of thermodynamic processes that have special properties. Number first is the adiabatic process. that is a process with no heat transfer into or out of the system. Number 2 is the isochoric process, that is a process with no change in volume, in which case the system does no work. Number 3 is the isobaric process, that is a process with no change in pressure. And number 4 is the isothermal process, that is a process with no change in temperature. Coming to the next part of today's lecture, that is the state of a system and state variables. A thermodynamic state is the macroscopic condition of a thermodynamic system as described by its particular thermodynamic parameters. The state of any thermodynamic system can be described by a set of thermodynamic parameters such as temperature, pressure, density, composition independently of its surroundings or history. The parameters required to specify the state depend on the characteristics of the system. There is an optimal ensemble of parameters that uniquely specify the state, and all other parameters can be derived from these. The state postulate says that the state of a simple compressible system is completely specified by two independent intensive properties. For thermodynamics, a thermodynamic state of a system is its condition at a specific time that is fully identified by values of a suitable set of parameters known as state variables or state parameters or thermodynamic variables. A thermodynamic system is a macroscopic object, the microscopic details of which are not explicitly considered in its thermodynamic description. The number of state variables required to specify the thermodynamic state depends on the system and is not always known in advance of experiment. It is usually found from experimental evidence. Always the number is 2 or more, usually it is not more than some dozen. Though the number of state variables is fixed by experiment, there remains choice of which of them to use for a particular convenient description. A given thermodynamic system may be alternately identified by several different choices of the set of state variables. The choice is usually made on the basis of the walls and surroundings that are relevant for the thermodynamic processes that are to be considered for the system. Besides the thermodynamic variables that originally identify a thermodynamic state of a system, the system is characterized by further quantities called state functions, which are also called state variables, thermodynamic variables, state quantities or functions of state. In other words, a state variable is one of the set of variables that are used to describe the mathematical state of a dynamical system. Intuitively, the state of a system describes enough about the system to determine its future behavior in the absence of any external forces affecting the system. Models that consist of coupled first order differential equations are said to be in state variable form. They are uniquely determined by the thermodynamic state as it has been identified by the original state variables. It is likely that the term functions of state was used in a loose sense during the 1850s and 60s by those such as Rudolf Clausius, William Rankine, Peter Tate and William Thomson, and it is clear by the 1870s the term had acquired a use of its own. In 1873, for example, Willard Gibbs in his paper, that is Graphical Methods in the Thermodynamics of Fluids, states that the quantities V, B, T, U and S are determined when the state of the body is given, and it may be permitted to call them functions of the state of the body. A passage from a given initial thermodynamic state to a given final thermodynamic state of a thermodynamic system is known as a thermodynamic process. Usually, this is transfer of matter or energy between system and surroundings. In any thermodynamic process, whatever may be the intermediate conditions during the passage, the total respective change in the value of each thermodynamic state variable depends only on the initial and final states. Various thermodynamic diagrams have been developed to model the transitions between thermodynamic states. The following are considered to be state functions in thermodynamics. Number first is the internal energy, that is designated as capital U. Internal energy is a state variable that can be thought of as the energy of the system, sensible, latent, chemical bond, nuclear, etc. It is not obvious how to define it, and thus it is much easier to discuss changes in internal energy rather than absolute values, which is true of many state variables. Number second is the enthalpy, which is designated as capital H. Enthalpy is a state variable that is most easily thought of as heat energy, although strictly speaking it is only heat energy in a system that is at constant pressure and which experiences no other work other than constant pressure expansion. Number third is the entropy, which is designated as capital S. Entropy has many definitions, many of which are applicable under specific circumstances. We will think of S as a measure of disorder, that is, higher values of S are systems with greater disorder. Number fourth is the Gibbs free energy, which is designated as capital G. G is equal to H minus Ts, or equivalently G is equal to delta H minus delta Ts. G can be thought of as the energy relevant to chemical reactions and thus involves both enthalpy and entropy. A reaction is spontaneous if G is less than 0 for a reaction, that is, it can occur without the input of energy. To satisfy this requirement, a reaction can either stabilize molecules leading to H less than 0, or it can create greater disorder, that is, S is greater than 0, or both. Number fifth is the heat energy, which is designated as capital Q. The heat exchanged between a system and its environment for some change in state is a path variable. Number sixth is the work, which is designated as capital W. The work exchanged between a system and its environment for some change in state is a path variable. Now that we have understood about state of a system and state variables, let us now try to learn about intensive and extensive variables. A thermodynamic variable may be intensive or extensive. The variables which are independent of size or amount of substance are called intensive variables. Density is an intensive variable because it does not depend on the amount of that substance. The variables which depend on the size or amount of the substance are called extensive variables. It is additive for independent and non-interacting subsystems. Mass and volume are extensive variables because they are directly measuring the amount of substance. Coming to their properties. Thermodynamic properties are divided into two broad types, that is, intensive properties and extensive properties. An extensive property is any property that depends on the size or extent of the system under consideration. Volume is an example. If you double the length of all edges of a solid cube, the volume increases by a factor of 8. Examples of extensive properties include mass, volume, entropy, enthalpy, energy, stiffness, and particle number. On the other hand, an intensive property is any property that can exist at a point in space. Temperature, pressure, and density are good examples. You could imagine moving a thermometer about a room or a pressure sensor about a swimming pool so as to record the property at each location, that is, point in space. Examples of intensive properties include temperature, density, specific gravity, viscosity, velocity, and electrical resistivity. Next is the thermodynamic equilibrium. The two systems are said to be in thermodynamic equilibrium with each other when they are in mechanical, chemical and thermal equilibrium with each other. Let us suppose that there are two bodies at different temperatures, one hot and one cold. When these two bodies are brought in physical contact with each other, temperature of both the bodies will change. The hot body will tend to become colder while the cold body will tend to become hotter. Eventually, both the bodies will achieve the same temperature and they are said to be in thermodynamic equilibrium with each other. In an isolated system, when there is no change in the macroscopic property of the system like entropy, internal energy, etc., it is said to be in thermodynamic equilibrium. The state of the system which is in thermodynamic equilibrium is determined by intensive properties such as temperature, pressure, volume, etc. Whenever the system is in thermodynamic equilibrium, it tends to remain in this state infinitely and will not change spontaneously. Thus, when the system is in thermodynamic equilibrium, there won't be any spontaneous change in its macroscopic properties. Coming to the conditions for thermodynamic equilibrium. The system is said to be in thermodynamic equilibrium if the conditions for following three equilibrium is satisfied. Number first is the mechanical equilibrium, number second is the chemical equilibrium and number third is the thermal equilibrium. Now coming to the mechanical equilibrium. When there are no unbalanced forces within the system and between the system and the surroundings, the system is said to be under mechanical equilibrium. The system is also said to be in mechanical equilibrium when the pressure throughout the system and between the system and surroundings is same. Number second is the chemical equilibrium. The system is said to be in chemical equilibrium when there are no chemical reactions going on within the system or there is no transfer of matter from one part of the system to other due to diffusion. Two systems are said to be in chemical equilibrium with each other when their chemical potentials are same. Number third is the thermal equilibrium. When the system is in mechanical and chemical equilibrium and there is no spontaneous change in any of its properties, the system is said to be in thermal equilibrium. When the temperature of the system is uniform and not changing throughout the system and also in the surroundings, the system is said to be in thermal equilibrium. If any of the above conditions are not fulfilled, the system is said to be in non-equilibrium. At last, let us try to learn about the first law of thermodynamics. The first law of thermodynamics is a version of the law of conservation of energy adapted for thermodynamic systems. The law of conservation of energy states that the total energy of an isolated system is constant, that is, energy can be transformed from one form to another but cannot be created or destroyed. The first law is often formulated by stating that the change in the internal energy of a closed system is equal to the amount of heat supplied to the system minus the amount of work done by the system on its surroundings. Investigations into the nature of heat and work and their relationship began with the invention of the first engines used to extract water from mines. Improvements to such engines so as to increase their efficiency and power output came first from mechanics that tinkered with such machines but only slowly advanced the art. Deeper investigations that placed those on a mathematical and physical basis came later. The process of development of the first law of thermodynamics was by way of much investigative trial and error over a period of about half a century. The first full statements of the first law came in 1850 from Rudolf Clausius and from William Rankine. Rankine's statement was perhaps not quite as clear and distinct as was Clausius. According to Truesdell, 1980, Julius Robert von Mayer in 1841 made a statement that meant that in a process at constant pressure, the heat used to produce expansion is universally interconvertible with work. But this is not a general statement of the first law. The first explicit statement of the first law of thermodynamics by Rudolf Clausius in 1850 referred to cyclic thermodynamic processes. That is, in all cases in which work is produced by the agency of heat, a quantity of heat is consumed which is proportional to the work done, and conversely, by the expenditure of an equal quantity of work, an equal quantity of heat is produced. Clausius also stated the law in another form, referring to the existence of a function of state of the system, the internal energy, and expressed it in terms of differential equation for the increments of a thermodynamic process. This equation may be described as follows. In a thermodynamic process involving a closed system, the increment in the internal energy is equal to the difference between the heat accumulated by the system and the work done by it. Because of its definition in terms of increments, the value of the internal energy of a system is not uniquely defined. It is defined only up to an arbitrary additive constant of integration, which can be adjusted to give arbitrary reference zero levels. The revised statement of the first law postulates that a change in the internal energy of a system due to any arbitrary process that takes the system from a given initial thermodynamic state to a given final equilibrium thermodynamic state can be determined through the physical existence for those given states of a reference process that occurs purely through stages of adiabatic work. The revised statement is then, for a closed system in any arbitrary process of interest that takes it from an initial to a final state of internal thermodynamic equilibrium, the change of internal energy is the same as that for a reference adiabatic work process that links those two states. This is so regardless of the path of the process of interest and regardless of whether it is an adiabatic or a non-adiabatic process. The reference adiabatic work process may be chosen arbitrarily from amongst the class of all such processes. In short, we can say that the first law of thermodynamics is the application of the conservation of energy and principle to heat and thermodynamic processes. The change in internal energy of a system is equal to the heat added to the system minus the work done by the system. That is, delta U is equal to Q minus W, that is, change in internal energy is equal to the heat added to the system minus work done by the system. The first law makes use of the key concepts of internal energy, heat, and system work. It is used extensively in the discussion of heat engines. The standard unit for all these quantities would be joule, although they are sometimes expressed in calories. That's all about today's lecture. Hope you have understood it very well. Thank you very much and goodbye.